Imagine this, a spacecraft no bigger than a paperclip, racing through the cosmos at one-third the speed of light. Its destination? Not a nearby star, not even a distant planet, but the most mysterious, terrifying, and fascinating object in the universe, a black hole. This isn't science fiction. This is a real mission concept being explored by astrophysicists right now. And if it works, it could be the first direct probe of a black hole in human history. Today, we're breaking down this mind-bending idea. How a nanocraft could survive the journey, what it might discover, and why the attempt itself could change the future of space exploration forever. Part 1. Why aim for a black hole? Black holes have always been the ultimate scientific tease. They hide behind event horizons, devour anything that dares to get close, and warp space and time so much that our best physics struggles to keep up. We've imaged their shadows with the Event Horizon Telescope. We've detected their cosmic collisions through gravitational waves. But here's the truth. We've never gotten close enough to one to actually see what happens at the edge. A probe, sent directly toward a black hole, could settle some of the biggest questions in science. Do black holes really have event horizons? Or could there be something else, like a surface of exotic matter? Does Einstein's theory of general relativity still hold up under the most extreme gravity imaginable? What happens to light, time, and energy as you get closer to the point of no return? If we're serious about exploring the deepest mysteries of the cosmos, then black holes are the ultimate laboratory, and scientists now think they may have a way to reach one within a single human lifetime. Part 2. The nanocraft concept. Here's where the brilliance comes in. Instead of building a giant rocket, the plan centers on a nanocraft, a spacecraft that weighs only a few grams. Picture a microchip mounted on a thin reflective sail, lighter than a feather and thinner than paper. How do you launch something so small across interstellar space? Not with rockets. Rockets are too heavy, too slow, and would require impossible amounts of fuel. Instead, you use light itself. The nanocraft would be pushed by a powerful array of lasers on Earth. When these lasers hit the sail, their light pressure would accelerate the craft to nearly 100,000 kilometers per second, about a third the speed of light. At that velocity, a black hole 20 to 25 light-years away could be reached in just 70 years. The probe's data, transmitted at light speed, would take another 20 years to return to Earth. That means the entire round-trip mission launched to receiving the first black hole data could happen in less than a century. For interstellar travel, that's revolutionary. Part 3. Finding the right target. There's just one catch. The nearest confirmed black hole, called Gaia BH1, is more than 1,500 light-years away, way too far for this mission to be practical. So, scientists are betting that there are closer, hidden black holes in our galactic neighborhood. Many may be small, quiet, and undetected, lurking in the darkness. How do you find them? Two main strategies: tracking stellar motions. If a star wobbles oddly, it may be orbiting an invisible black hole. Gravitational lensing. Black holes bend the light of background stars. By spotting these distortions, astronomers can locate invisible objects. Upcoming surveys could reveal a black hole within that sweet spot of 20 to 25 light-years. Without it, this mission stays a concept. With it, the countdown begins. Part 4. The engineering challenges. Even if we find the perfect target, the mission faces obstacles that make Apollo look like child's play. Challenge 1. Survival in interstellar space. The nanocraft would spend decades exposed to cosmic radiation and high-speed dust particles. A single hit from a micrometeoroid could obliterate it. Designing a chip and sail that can survive for 70-plus years is no small feat. Challenge 2. Power and communication. How do you power instruments for decades without conventional fuel? And once you reach the black hole, how do you send meaningful data across 20 light-years of emptiness back to Earth? These are problems that require radical innovation in miniaturized electronics and communication. Challenge 3. The laser array. This is the monster challenge. The propulsion system would require a ground-based laser array so powerful it could accelerate the nanocraft to a third of light speed. Right now, the cost of such an array is estimated at around 1 trillion euros. But scientists like Cosmo Bambi believe advances in laser efficiency and energy production could slash that cost to around 1 billion euros within a few decades. That's expensive, but no longer science fiction. It's within the ballpark of modern space missions. Part 5. What we could discover now. Let's imagine it works. The Nanocraft reaches a black hole. What could it actually see and measure? Event horizon. Physics. General relativity predicts a sharp boundary where nothing escapes. But some alternative theories propose exotic matter or quantum effects at the edge. A close probe could give us direct evidence for one or the other. Time dilation and gravitational redshift. Near the event horizon, time itself slows down relative to distant observers. Light stretches to longer wavelengths. Measuring this directly would be a test of Einstein's theory on a cosmic scale. Accretion flows and magnetic fields. The swirling matter around black holes is one of the most violent environments in the universe. A probe could give us the clearest picture yet of how black holes feed and power jets that span entire galaxies. Quantum gravity clues, perhaps the most exciting possibility, finding evidence of new physics. If black holes deviate even slightly from Einstein's predictions, it could point the way to a deeper theory that unites general relativity with quantum mechanics. Part 6. Spin-off technologies. Even if the probe never makes it to a black hole, the mission would push technology forward in huge ways. Laser propulsion could open the door to interstellar travel on human timescales. Suddenly, sending probes to nearby stars in decades, not millennia, becomes possible. Miniaturized deep space instruments would cut mission costs and allow swarms of probes instead of just one. Radiation-resistant materials developed for the Nanocraft could be applied to satellites, space stations, and even industries here on Earth. This is why scientists emphasize the mission's value isn't just in reaching a black hole. The path toward it could transform space technology across the board. Part 7. A generational effort. Let's be real, this mission won't launch next year, or even in the next decade. It's a long-term, generational project. Step 1 is finding the right black hole. Step 2 is testing Nanocraft on shorter missions, maybe to the outer solar system. Step 3 is building and scaling up the laser array. The scientists who start this project may not live to see its completion, but that's nothing new in astronomy. Gravitational waves were predicted in 1916. We didn't detect them until 2015. The first black hole image was dreamed about for decades,